So, good day everyone. We're going to discuss about the multi-threaded programming, chapter 4. So, what is multi-threaded programming? So, it is mainly found in multitasking operating systems. It is also a widespread programming and execution model that allows multiple threads to exist within the context of one process. This is the chapter objectives of multi-threaded programming, chapter 4. Is to introduce the notion of a thread, a fundamental unit of CPU utilization that forms the basis of multi-threaded computer systems. Second is to discuss the APIs for the pthreads, Win32 and Java thread libraries, and lastly to examine the issues related to multi-threaded programming. So, thread is a basic unit of CPU utilization. It means the program under execution is a process, and each process has a number of threads executed in it. So, ang thread, it comprises thread ID, program counter, a register, and a stack. It also shares with other threads belonging to the same process such as code section, data section, and other operating systems such as open files and signals. Again, this is what the thread comprises apart from that. The thread shares these things, code section, data section, and other operating systems are shared between threads belonging to the same process. The process contained thread will share resources like open files, signals, code section, data section, and other things, which means it only has a one thread of control. So traditional heavyweight processes have a single thread of control. There is one program counter and one sequence of instructions that can be carried out any given time. So here, let's understand the single-threaded and the multi-threaded process. So in the first diagram, you will see the single-threaded process, which we refer to it's a traditional or a heavyweight process having a single thread of control. So this whole block consists of a one thread which have a code section, data section, files, registers, and stacks belonging to this process. So there is only one thread that this block process can perform only one task at a time, while the other one is the multi-threaded process. It is a single process which it has a three-threaded process, so 1, 2, 3. Each of these threads have their own stacks and registers. In the top, you will be able to find the code section, data section, and files belonging to this process, and it is shared by 3 threads. In this case, multi-threaded process can perform multiple tasks at a time. Each thread perform different tasks, and multiple tasks can perform at a time by the help of the multi-threaded process. So, threads are very useful in modern programming. Whenever a process has a multiple tasks to perform independently of the others, this is particularly true when one of the tasks may block and it's desired to allow the other task to proceed without blocking. So, for example, is word processor a web server? Sa word processor, may have a thread for displaying graphics na po siya thread na keystrokes from the user o lain po na thread for performing spelling and grammar checking in the background. So for the explanation of multi-threaded server architecture is to have the server run as a single process that accepts requests. When the server receives a request, it creates a separate process to service that request. In fact, this process creation method was in common use before threads became popular. It is generally more efficient to use one process that contains multiple threads. If the web server process is multi-threaded, the server will create a separate thread that listens for client request. When a request is made, rather than creating another process, the server will create a new thread to the service the request and resume listening for additional requests. So that is the multi-threaded server architecture. So these are the four major categories of benefits to multi-threading: responsiveness, resource sharing, economy, and scalability. So the first one is responsiveness, which is the multi-threading. An interactive application may allow a program to continue running even if part of it is blocked or performing a lengthy operation, thereby increasing responsiveness to the user. For example of that is kanang input at output sa user. Next is the resource sharing. It is the process may only share resources through techniques such as shared memory or message passing. Such techniques must be explicitly arranged by the programmer. However, threads share the memory and the resources of the process to which they belong by default. So, the benefit of sharing the code and data kay ma-allow siya na ang application to have several different threads within the same address space. So, economy is allocating memory and resources for process creation is costly because threads share the resources of the process to which they belong. It is much more economical to create and context switch threads. So, for example, is kanang creating a process na about 30 times slower is creating the thread, while ang context switching is about 5 times slower. And next is scalability. The benefits of multi-threading can be greatly increased in a multiprocessor architecture, where threads may be running in parallel on different processors. A single-threaded process can only run on one processor, regardless how many are available. So, multi-core programming. A recent trend in computer architecture is to produce chips with multiple cores, or CPUs on a single chip. Threads or processes are concurrent when they execute at approximately the same time. This can happen on a computer with a single CPU. For example, is the operating system performs multitasking. However, parallel threads or processes truly execute simultaneously. This can only happen on a multiprocessor. So in this part, we're going to discuss ni ang concurrent execution on a single core system sa multiprogramming o ang parallel execution on multi-core system. So mo ni siya ang multi-core programming, concurrent execution on a single core system o ang parallel execution on multi-core system. So sa single computing core system kay it means na the execution of the thread will be intervaled over time. So ang kaya lang ani niya na ma-execute is only one thread at a time, while ang parallel kay gina-assign niya separate to each core 1 o core 2, which kanang it enables the thread to run in parallel. So towards the parallel execution on a multi-core system has placed pressure na system designers as well as application programmers, because to make it better use of multi-computing cores, this one. So dividing activities. So kani siya ang sa isa ka task ma-divide siya tagsa-tagsa, and through the parallel execution kaya niya mabuhat ang isa ka task or duha ka task dungan. Next is the balance. While identifying the tasks that can run in parallel, programmers must also ensure that the tasks perform equal work of equal value. In some instances, a certain task may not contribute as much value to the overall process as others. Kana pong separate execution sa isa ka core, mag-run na siya, dili kayo worth ang cost if so data splitting. Just as applications are divided into separate tasks, the data accessed and manipulated by the task must divided to run on separate cores. So muna siya tong parallel execution ng multi-core system where separate cores kay garon dungan. Data dependency. The data accessed by the task must be examined for dependencies between two or more tasks. For the testing and debugging, when a program is running in parallel or on multiple cores, there are many different execution paths. Testing and debugging such as concurrent programs is inherently more difficult than testing and debugging single-threaded applications. So, mao to siya ang programming challenges na sa isa ka multi-threaded programming.
Let's go to 4.2 multithreading models. As a definition, support for threads may be provided either at the user level for user threads or by the kernel threads for kernel threads. User threads are supported above the kernel and are managed without kernel support, whereas kernel threads are supported and managed directly by the operating system. Virtually all operating systems, including Windows XP, Linux, Mac OS X, Solaris, and 364 Unix support with kernel threads. There are two types of threads. First is the user-level threads, which user-managed threads. Thread library contains code for creating and destroying threads, for passing message and data between threads, for scheduling thread execution, and for saving and restoring thread context. The second one is the kernel level threads, where the operating system manages threads acting on kernel and operating system core. Any application can be programmed to be multi-threaded. All of threads within the application are supported with a single process. It also maintains context information for the process as a whole and for individual threads with the process. There are three types of multi-threading models: the one-to-one model, the many-to-one model, and the many-to-many model. But first, let's discuss about the many-to-one model, where it maps many user-level threads to one kernel thread. Thread management is done by the thread library in a user space. It's efficient, but the entire process will block if a thread makes a blocking system call. This picture is same as the other picture. So we have the one kernel thread and the 4 user threads, and this explains that only one thread can access the kernel at a time, so multiple threads are unable to run the parallel on multiprocessor. Second one is one-to-one model. It maps user thread to a kernel thread. It provides more accuracy than the many-to-one model by allowing another thread to run. When a thread makes a blocking system call, it allows multiple threads to run in a parallel on multiprocessor. So nagbulag-bulag sila, wala sila nagkatong sikip-sikip. So we have one kernel thread and one user thread. The disadvantage of it is this model is creating user thread requires the corresponding kernel thread. OS 2 Windows NT and Windows 2000 use 1-to-1 relationship model. The third one is the many-to-many model. It multiplexes many user threads to smaller or equal number of kernel threads. The number of kernel threads may be specific to either a particular application or a particular machine. We have here the 3 kernel threads and the 4 user threads. Same as here, we have 6 kernel threads and the 3 user thread, 3 user thread, where 6 user-level threads are multiplexing with 6 kernel-level threads. In this model, developers can create as many user threads as necessary, and the corresponding kernel threads can run in the parallel on multiprocessor machine. This model provides the best accuracy and currency, and when the thread performs blocking system call, the kernel can schedule another thread for execution. The one popular variation of the many-to-many model still multiplexes user-level threads to a smaller or equal number of kernel threads, but also allows a user-level thread to be bound to a kernel thread. This is referred as the two-level model. We have here 3 kernel threads and 4 user threads, and the other one is katong mura siyang isa kernel thread and isa ka user thread. That's all for multi-threading models. Summary 4.6. A thread is a flow of control within a process. A multi-threaded process contains several different flows of control with the same address space. The benefits of multi-threading including increased responsiveness to the user, resources sharing with the process economy, and scalability. We have summary 4.6. A thread is a flow of control within a process. A multi-threaded process contains several different flows of control with the same address space. The benefits of multi-threading include increased responsiveness to the user, resource sharing with the process economy, and scalability issues such as more efficient use of multiple cores. User-level threads are the threads that are visible to the program and are known to the kernel. The operating system kernel supports the managed kernel-level threads. 3 different types of model relate user and kernel threads. We have the many-to-one models, one-to-one models, and many-to-many models. Many-to-one models that maps many user threads to single kernel, and one-to-one models that maps each user thread to a corresponding kernel thread. A many-to-many model multiplexes many user threads to a smaller or equal number of kernel threads.
Thread libraries. Thread libraries provide programmers with API for creation and management threads. Thread libraries may be implemented either in user threads or kernel threads. It also provides the programmer with an API for creating and managing threads. There are 2 ways of implementing a thread library. It's user threads or kernel threads. In user thread, it involves API functions implemented solely within the user space with no kernel support. These are the threads that application programmers use in their programs. All code and data structures for the library exist in user space. This means that invoking a function in the library results in a local function call in user space and not a system call. In the kernel thread, it involves system calls and requires a kernel with the thread library support. All modern OS support kernel-level threads, allowing the kernel to perform multiple simultaneous tasks and or service multiple kernel system calls simultaneously. It implements a kernel-level library support directly by the operating system. In this case, code and data structures of the tree library exist in kernel space. Invoking a function in the API for the library typically results in a system call to the kernel. 3 main thread libraries: POSIX pthreads, Win32 threads, and Java threads. POSIX pthreads refers to the POSIX standard defining an API for thread creation and synchronization. This is a specification for thread behavior, not implementation. Operating system designers may implement the specification in any of they wish. Numerous systems implement the pthread specification, including Solaris, Linux, Mac OS X, and True64 Unix. Shareware implementations are available in the public domain for the various Windows operating systems as well. Pthreads also. The C program shown in the figure 4.9, the basic Pthreads API for constructing a multi-thread program that calculates the summation of a non-negative integer in a separate in Win32 threads. The technique for creating threads using the Win32 thread library is similar to the pthreads technique in several ways. We illustrate the Win32 thread API in the C program shown in figure 4.10. Notice that we must include the windows.h header file when using the Win32 API. In figure 4.10, multi-threaded C program using the Win32 API. Threads are created in Windows 32 API using the create thread function, and just as a pre-thread set of attributes for that thread is passed to this function. These attributes is included in security information, the size of the stack, and a flag that can be set to indicate if the thread is to start in a suspended state. In this program, we use the default values for these attributes, which do not initially set the thread to a suspended state and instead make it eligible to be RM1 by the CPU scheduler. And lastly, Java threads. Threads are the fundamental model of program execution in Java program, and the Java language and its API provide a rich set of features for the creation and management of threads. All Java programs comprise at least a single thread of control. Even a simple Java program consisting of only main method runs as a single thread in JVM. Two techniques for creating threads in Java. One approach is to create a new class that is derived from the thread class and to override its run method. An alternative and more commonly used technique is to define a class that implements the runnable interface. The runnable interface is defined as follows. In Java threads, creating a thread does not specifically create the new thread. Rather, its start method that creates the new thread. Calling the start method for the new object does the two things. It allocates memory and initializes a new thread in the Java virtual machine. It calls the run method, making thread eligible to run by the Java virtual machine. And that's it. Thank you.
In Chapter 4, Lecture 4, we will discuss about threading issues. So we have some implementation issues with threads at the time of forking and executing. These two systems call both change in multi-threaded program. So what are the issues with fork is that when we are working a process, then the new process which is produced should duplicate all threads, and also it should just duplicate only that thread. For that reason, there are two types of forking process, one that duplicates all threads and the other is that duplicates only the thread that invoke the forking call system. And the same way as executing works. If a thread invokes the exec system call, the program specified in the parameter to exec will replace the entire process including all threads. So if a thread invokes the exec system, then the program is specified in that parameter to exec. The exec function will invoke only that lubricate packet, or it will execute only that process. The JVM and the host operating. The JVM is typically implemented on the top of a hosting operating system. This setup allows the JVM to hide the implementation details of the underlying operating system and to provide a consistent, abstract environment that allows Java programs to operate on any platform that supports a JVM. The specification for the JVM does not indicate how Java threads are to be mapped to the underlying operating system, instead leaving that decision to the particular implementation of the JVM. So the next thing that we would talk about is cancellation. Thread cancellation is the task of terminating a thread before it has completed. For example, if multiple threads are concurrently searching through a database and one thread returns the result, the remaining threads might be cancelled. Another situation might occur when a user presses a button on a web browser that stops a web page from loading any further. Often, a web page is loaded using several threads. Each image is loaded in a separate thread. When a user presses the stop button on a web browser, all threads loading the page are cancelled. Target thread is the task of terminating a thread before it has completed. Main scenario is that if the process is terminated, then what should be the cancellation scenario of different type of threads? If this process is having different thread and now this process itself is cancelled, how this thread should be entered? For that, we have two different type of cancellation schemes. One is asynchronous cancellation and the second one is deferred cancellation. In asynchronous cancellation, one thread immediately terminates the target thread, while the deferred cancellation, the target thread periodically checks whether it should be terminated, allowing it an opportunity to terminate itself in an orderly fashion. Difficulty occurs if the thread is being executed or resources have been already allotted to it, especially in asynchronous cancellation. In asynchronous cancellation, always reclaim system resources from a cancelled thread but will not reclaim all resources, while in the deferred cancellation, it is done using flag whether it is to be cancelled or not. It checks the flag whether it should be cancelled at a point, then it can be cancelled safely. This is called as cancellation points. Let's proceed to signal handling. Signal is used in Unix systems to notify a process that a particular event has occurred. A signal may be received either synchronously or asynchronously depending on the source of and the reason for the event being signaled. Synchronous signals delivered to the same process that performed the operation that caused the signal. That is the reason they are considered synchronous. Examples of synchronous signal are illegal memory access and division by zero. Asynchronous signals when a signal is generated by an event external to a running process. Examples of asynchronous signal terminating a process with specific keystrokes such as Control-C and having a timer expire. All signals, whether synchronous or asynchronous, follow the same pattern. There are three concepts. First is a signal is generated by the occurrence of a particular event. Second is a generated signal is delivered to a process. And the third, once delivered, the signal must be handled. A signal may be handled by one of two possible handlers. First, a default signal handler run by the kernel when handling that signal. The action that a script or program performs when it receives a signal is called the default action. The second one is a user-defined signal handler. Can be overridden a default signal handler. Our next topic is all about thread pools. In multithreading a web server, in this situation, whenever the server receives a request, it creates a separate thread to service the request. Whereas creating a separate thread is certainly superior to creating a separate process. A multi-threaded server has potential problems. The first issue concerns the amount of time required to create the thread prior to servicing the request, together with the fact that this thread will be discarded once it has completed its work. The second issue is more troublesome. If we allow all concurrent requests to be serviced in a new thread, we have not placed a bound on the number of threads concurrently active in the system. Unlimited threads could exhaust the system resources, such as CPU time or memory. One solution to this problem is to use a thread pools. What is thread pools? Thread pools creates a number of threads at a process startup and place them into a pool where they sit and wait for work. How does thread pool works? When a server receives a request, it awakens a thread from this pool. After that, if one is available and passes it the request for service. Once the thread completes its service, it returns to the pool and awaits more work. If the pool contains no available thread, The server waits until one becomes free. Thread pools offer these benefits. First, servicing a request with an existing thread is usually faster than waiting to create a thread. Second, a thread pool limits the number of threads that exist at any one point. This is particularly important on systems that cannot support a large number of concurrent threads. The number of threads in the pool can be set heuristically based on factors: the number of CPUs in the system, the number of physical memory, the expected number of concurrent clients requests. More sophisticated thread pool architectures can dynamically adjust the number of threads in the pool according to the usage pattern. Such architectures provide the further benefit of having a small pool, thereby consuming less memory when the load on the system is low. Now let's talk about thread-specific data. Threads belonging to a process share the data of the process. Indeed, this sharing of data provides one of the benefits of multi-threading programming. However, in some circumstances, each thread might need its own copy of certain data. We will call such data as thread-specific data. For example, in a transaction process system, we might service each transaction. For example, in a transaction process system, we might service each transaction in a separate thread. Furthermore, each transaction might be assigned a unique identifier. To associate each thread with its unique identifier, we could use thread-specific data. Lightweight process, or LWP. Many systems implementing either the many-to-many or the two-level model place an intermediate data structure between the user and kernel thread. This data structure typically known as a lightweight process or LWP. Each LWP is attached to a kernel thread, and it is kernel threads that the operating system schedules to run on physical processors. If a kernel thread blocks, such as while waiting for an I/O operation to complete, the LWP blocks as well. Up the chain, the user-level thread attached to the LWP also blocks. And that one scheme for communication between the user thread library and the kernel is called as scheduler activations. So how does it works? The kernel provides an application with a set of virtual processors, and the application can schedule user threads into an available virtual processor. The kernel must inform an application about certain events. This procedure is known as app call. App calls are handled by the thread library with an app call handler, and the app call handlers must run on a virtual processor. Note: one event that triggers an app call occurs when an application thread is about to block. The kernel makes an app call to the application informing it that a thread is about to block and identify the specific thread. The kernel then allocates a new virtual processor to the application. The application runs an app call handler on these new virtual processors, which saves the state of blocking thread and relinquishes the virtual processors on which the blocking thread is running. The app call handler then schedules another thread that is eligible to run on the new virtual processor. When the event that the blocking thread was waiting for occurs, the kernel makes another app call to the thread library informing it that the previous blocked thread is now eligible to run. The app call handler for this event also requires a virtual processor, and the kernel may allocate a new virtual processor or preempt one of the user threads and run the app call handler on its virtual processor. And lastly, after marking the unblocked thread as eligible to run, the application schedules an eligible thread to run on an available virtual processor.
The next topic is 4.5 Operating System Examples. Based on the referred book, there are two examples of operating system. First example is the Windows XP thread, and the second is Linux thread. What is Windows XP thread? Windows XP implements the Win32 API, which is the primary API for the family of Microsoft operating systems. Indeed, much of what is mentioned in this section applies to this entire family of operating system. To give a background, what this Win32 API is, It is a Windows application programming interface for developing 32-bit application. We all know that Microsoft runs a 32-bit application of C++ programming language. Next, Windows XP uses the one-to-one model for thread mapping. And Windows XP application runs as a separate process, and each process may contain one or more threads. Next, the general component of a thread include a thread ID uniquely identifying the thread, a register set representing the status of the processor, a user stack employed when the thread is running in user's mode, and a kernel stack employed when the thread is running in kernel mode, and a private storage area used by virus, runtime libraries, and dynamic link libraries. The register set, stacks, and the private storage area are known as the context of the thread. The primary data structure of a thread include the E thread, which is the executive thread block, K thread, the kernel thread block, and tab is the thread environment block. You can see this is the data structure of a Windows XP thread. The essential component of the E thread include the pointer to the process to which the thread belongs and the address of the routine in which the thread starts control. The E thread also contains the pointer to the corresponding K thread. The K thread includes scheduling and synchronizing information for the thread. In addition, K thread includes the kernel stack and a pointer to the tab. The E thread and the K thread exist entirely in kernel space, which this means that only the kernel can access them. The tab is a user space data structure that is accessed when the thread is running in user's mode. Among other fields, the tab contains the thread identifier, a user's mode stack, and an array for the thread local storage. The next example is the Linux thread. Linux provides the fork system call with the traditional functionality and duplicating a process. Linux also provides the ability to create threads and by using the clone system call. Linux generally uses the term task rather than the process or thread when referring to a flow of control within a program. The Linux kernel does not provide any special scheduling semantics or data structure to represent threads. Instead, the thread is merely a process that shares certain resources with other processes. When clone is invoked, it is passed a set of flags which determine how much sharing is to take place between the parent and the child task. Some of these flags are listed below. For example, if clone is passed the flag clone fs, clone vm, clone sighand, and clone files, the parent and the child task will share the same file system information, same memories, same signal handlers, and same set of open files. However, if none of these flags is set when clone is invoked, no sharing takes place. When fork is invoked, a new task is created along with a copy of all the associated data structures of the parent process. A new task is also created when the clone system call is made. However, rather than copying all data structures, the new task points to the data structure of the parent task depending on the set of flags passed to clone.
Summary 4.6. A thread is a flow of control within the process. A multi-threaded process contains several different flows of control with that same address space. The benefits of multi-threading include increased responsive to the user, resource sharing with the process economy and stability issues as more efficient use of multiple cores. User-level threads are the threads that are visible to the programmer and unknown to the kernel. The operating system kernel supports and manages kernel-level threads. Three different types of models relate user and kernel threads. We have the many-to-one models, one-to-one models, and many-to-many models. The many-to-one models that maps many user threads to a single thread, and one-to-one models that maps each user thread to a corresponding kernel thread. And the many-to-many model multiplexes many user threads to a smaller or equal number of kernel threads. And that's all for